During the next 18 minutes, take no notes. Because during the next 18 minutes, I'm going to solve this differential equation for you, and I have decided, which I not always do, to do it exactly the way that French does it. Very elegant. So if you take notes, you're wasting your time because you have it in your book. And I would much rather prefer that you follow each step that I make, so you have more time to concentrate on the method. So don't write anything down. That is my recommendation. 18 minutes. You can time me if you don't believe me. We're going to jump to the complex plane. This is a beautiful example where the complex solutions really come in handy. And so I'm going to change this equation to z, which is now a complex notation. Z double dot plus gamma z dot plus omega 0 squared times z equals 0. And then z, my trial function, is some amplitude a times e to the power j p t plus alpha. Now clearly this has the smell of an amplitude, and this here has the smell of a frequency. Anything e to the power j pt has the smell of a frequency. But you will see that you're in for a surprise, what happens with this p. Once we have found the proper solution to z, we take the real part and we are in business. Then we go back to x. I'm going to take the second derivative of this equation. So out comes, jp comes out twice, so that is j squared times p squared. And so I'm going to see now minus p squared. That is the second derivative of this function, and the z comes later. Then I have plus gamma, and then what pops out is jp, because it's only the first derivative. jp. You have to be very careful that you can distinguish your j's from your gammas. And then you get plus omega 0 squared, and the whole thing times z, and that now must be equal to 0. Well, if you have an equation like this, you may think it's one equation, but it really is two equations. Because if something like this has to be 0, and of course z is 0, is not an acceptable solution, because that's the oscillation. If you have an equation like this, which has a real part, and it has an imaginary part, then both must independently be 0. Obvious reasons. These are apples, and these are oranges, and 5 apples minus 5 oranges is never 0 oranges, is never 0 apples. You cannot subtract apples from coconuts. So this has to be 0, and this has to be 0. Now, if you make gamma 0, you have no problem. There is no damping, so that's ridiculous. If you make p 0, then you no longer have any oscillation going on, because you smell that pt, that's going to be the oscillatory thing. So that's also unacceptable. And so this won't work. Therefore, p itself must be complex. And so we're going one step further now, and we're going to say, the only way that we could make this work is if we say p equals n plus js, whereby n and s then, let's hope, are real. So let's first calculate what p squared is. So we go slowly, so we don't get into trouble with the algebra. So p squared is n squared plus this one squared, the j squared is minus 1, so that is minus s squared, plus 2n times j times s. So now I can go back to this form and have minus p squared. So I get minus n squared That is this minus p squared plus s squared minus 2n j times s. So I'm done here. Now I get gamma jp plus gamma times j. And now I have to multiply that by p, which is n, plus gamma times j times js. And then I have plus omega 0 squared. And this now has to be 0. I have here j square. J square is minus 1. So, I can erase this and replace it by minus gamma s. You cannot do that. That's the price you pay if you didn't take my advice not to take any notes. So this is minus gamma s. And now, this has to be 0. That means the apples must add up to 0. These are the apples. And the oranges have to be 0. This is an orange, this is an orange, this is an orange, and this is an orange. For this to be 0, there's a j here, there's a j here, there's an n here, there's an n here. 2s must be gamma. So gamma over 2 is s. Oh, we found s. For this to be 0, we find that n squared minus n squared plus gamma squared over 4, because we know what s is now. So plus gamma squared over 4 minus gamma over 2 times minus gamma times s, which is minus gamma squared over 2 minus gamma squared over 2 plus omega 0 squared equals 0. And that means that n squared is omega 0 squared minus gamma squared over 4. So we also have n. So we now have n, and we have s. And so now I can go back to my trial function, and I can substitute the values that we have found in that complex function. So we get z equals a times e to the power j. And now we have to put in pt plus alpha. But p is n plus js. So nt plus jst plus alpha. Yeah, and go slowly, I don't skip too many steps. But I know that s is gamma over 2. But I know that j square is minus 1. So therefore, this part here and this part here can be brought out. So we get a times e to the minus gamma over 2 times t. Here we have the t, the j square makes it the minus, and s is gamma over 2. And then I get e to the power j times nt plus alpha. The first thing that you see here, which is amazing, this term here is an exponential decay in time. There's nothing oscillatory about it. It means that this A, which is the original amplitude, is gradually dying out with a decay time, tau, which is 2 divided by gamma. Now remember, gamma has units second minus 1, so this really has units time. So this one is going to be responsible for that decay that we discussed earlier. What is this now? E to the power jnt. Well, n is obviously a frequency. This is the striking example in the complex plane of a rotating vector, and the angular frequency is n, but we know what n is. And so this n really is nothing but omega squared. N squared is really omega squared. And so I can replace this n now by whatever you have here. And so if I write this now, a e minus gamma over 2, I can write down now j omega t plus alpha, and I know exactly now what that omega is. That is the square root of this number. And so therefore omega squared is omega 0 squared minus gamma squared over 4. So those of you in the audience who intuitively sense that the frequency would go down because of the friction, they were right. See, omega is lower than omega 0. Now, of course, if gamma is very low, the two could be close together. Depends on gamma, that's obvious. If you have a lot of friction, then omega will be a lot less than omega 0. If you have very little friction, well, then they will be very closely the same. And so we can now write down in all its glory the real part of this function, which then becomes x equals some amplitude a times e to the minus gamma over 2 times t times e to the minus j times omega t plus alpha. Look what I did. I have an equation in the complex plane. That's perfectly okay. And then I went back to the real world, going from z, the complex plane, to the real part of z. And what did I write down? This is fine. But then I wrote down e to the power minus j omega t plus alpha. Now, first of all, there should not be a minus sign in front of the j. That's not a major problem. But I do not take it out of the complex plane. I leave it into the complex plane. So, clearly what I should have written, which is what I will do now, x equals a times e to the minus gamma over 2 times t times the cosine of omega t plus alpha. Now, we are in the real world. You're going to see this equation at least for the next 5 or 10 minutes on the tape. It is a thorn in my side, but there is nothing I can do about it. You just have to live with it and think of it as being this. And there are 2 adjustable constants which depend entirely on the initial condition. At time t equals 0, there are 2 things you can do to the object. You can bring it to a certain point away from equilibrium, and you can give it a kick. We call that a velocity. And you're free to choose any way you want to do that. And so it's clear that with those 2 choices that you have, that in your final solution, you end up with 2 adjustable constants which depend on the initial condition. And so you see that this amplitude is going to die out with a 1 over e decay time of 2 over gamma seconds, and that the frequency is lower than the frequency of the undamped system. I try to make a plot. So here is t, and here is x. And to guide my hand, I'm going to first put in this exponential. And now I'm going to put in that oscillatory term here, whereby the frequency is uniquely determined. Omega is uniquely determined. And the period t is that omega divided by 2 pi. Oops! How could I? Look what I wrote. I wrote t equals omega divided by 2 pi. It was not my day. Clearly, it should have been t equals 2 pi divided by omega. Now, Fortunately for me, very shortly afterwards, I erased this from the blackboard, so you won't see it for very long. In any case, this is what it should be. And therefore, I'm going to put in here 0 crossings to guide myself so that I don't make the mistake, which you often see, that people think that this period is slowly getting shorter in time. That is not true. It is the amplitude that decays away. And so if we now try to put in the oscillation, then this is what's going to happen. And so you see that the oscillation dies away in time, but the period t is uniquely determined, and that depends on how much friction there is. It is not uncommon to introduce a quality factor, Q, that is high if there is little damping, and that is low if there is a lot of damping. And that Q, which is dimensionless, is omega 0 divided by gamma. You see immediately if gamma is high, then Q is low. It's a low quality oscillator. If you introduce that, you can go back to your omega square equation, and then omega squared becomes omega 0 squared times 1 minus 1 divided by 4Q squared. Is this any different from that? No, it's just a different way of writing it because you introduce this. What it tells you is that if Q is about 10, and I bet you the Q's are much higher for these pendulums, then you have here 1 divided by 400, that is 1/4%, but since omega is the square root of that, it's only 1/8%. So for Q of 10, omega is only 1/8% lower than omega 0. Even if you make the Q as low as 2, the frequencies are only off by about 3.2%. So I want you to appreciate that most of the time, but not always, is omega very close to omega 0. We can look at the decay in a different way. Oh, we cannot do that here. I will do that here on the center board because we don't need that anymore. Instead of saying I have to wait 2 over gamma seconds for the amplitude to go down by a factor of E, I can ask myself, how many oscillations do I have to wait for the amplitude to go down by a factor E? How many oscillations? Well, n oscillations would take this long, t being the period of one oscillation. But for reasonable values of Q, t and t0 are the same, like omega and omega 0 are closely the same. So I can write for this that this is approximately n times t0, so that's approximately n times 2 pi divided by omega 0. I can now substitute this time in this t and only concentrate on that decay portion, that early part. So what I find then that A, after n oscillations, is A times e to the minus gamma over 2t, e to the minus gamma over 2, times this time after n oscillations, n divided by 2 pi divided by omega 0. And you lose a 2, but omega 0 divided by gamma is Q, and so now you have it in a form which is minus n times pi over Q. Now, is this any different from what we had before? No. Here we say I have to wait 2 over gamma seconds for the amplitude to go down by a factor of e. Here we say, if n is q divided by pi, then the amplitude goes down by 1 over e. So in one case, I ask myself, how many seconds do I have to wait? In the other case, I ask myself, how many oscillations do I have to wait? And so if q is 10, it tells you that you have to wait about 3 oscillations, roughly, for the amplitude to go down by a factor of e. And if q is 100, you have to wait more like 32 oscillations for the amplitude to go down by a factor of e. 18 minutes are up. So now you can start taking notes again. I have here 2 pendulums, and the pendulums have about the same length,